Is it okay if it's like two truths, one lie again?
Maybe if we have time. Usually it's more like a beginning of the year thing because it helps us kind of understand what it is we're doing.
I love the sound of crushing smoothie. Oh, did you win the last?
Satisfying, huh?
Oh. It just sounds so good.
Thanks. All right. Okay, well, crushing aside, if we're ready, are we ready?
Yeah.
Everybody ready? Okay, cool. Let's go. Let's get going today. Let me tell you guys though, lab today, I just want to give you a heads up, and I'm going to say it again before we start lab. This lab is a complex lab. It has a lot of steps, and you have to be very careful that you're reading very carefully the whole time. Like read all the steps really carefully. Make sure that you're following all the steps very carefully, because it's easy to mess something up. And you don't want to mess something up because then you're the whole thing, and you probably won't have time to start it over because it's a lot. Okay, so I just wanted to give you all a heads up on that. Here we go. All right, let's see. So we're going to talk today about classifying matter. First, somebody define matter for me. What's matter? Eunice.
Is the amount of mass in an object.
Yeah, that's one way to define it. Anybody else have a different definition? Annabelle?
Yeah, it's basically like just something that or another way to put it is just like something that takes up space.
Yes, anything that has mass and takes up space. There we go. Anything that has mass and takes up space.
Like that telephone thing that looks like Commander Tartar.
Yep, there's matter. Okay, so what is matter made of? All right, so all matter in the universe is made up of over 100 substances called what? Okay, Eunice.
Elements.
Elements. All right. Now, you can see he kind of has a sort of periodic table looking thing behind him. And when we start really talking about elements, there'll be a big vinyl periodic table that covers the whole fireplace. It's huge and it goes up right here. And we'll be using that to reference. Now, you've probably heard there's a song. You can go to YouTube and find it. I think you can go to Spotify, but it's the Element song.
The elephant.
Elephants, yeah. Element song. Have you heard it? Hydrogen and helium, yeah, it's and every year when I do chemistry, somebody asks me, "Can I learn that song?" And I'm like, "If you want to, knock yourself out. You can learn it." It familiarizes you with the names of the elements, but it doesn't really give you any useful information. The table is a tool, and it tells you information about all of the elements so that you don't have to memorize them, which is the point. Like, you don't need to memorize them. And you kind of need to know like where they're situated on the table because their position matters. So if you want to familiarize yourself with the elements, you can sure learn the song, but the best thing to do is to get familiar with the table. And we'll get real familiar with it because you're going to see a lot of it.
I already know this table, don't you?
Yeah, different kind of, I mean like a chart style of table. So before scientists recognized the elements we know today, what did they consider elements to be in the past? Okay, Emerson. Earth, wind, fire, water. So these are what you'd call like the classical or ancient elements. People used to say that everything was either made of earth, of wind, of fire, of water. So sometimes you'll hear this brought up like when you study mythology or any kind of fiction story that involves mythology or ancient stuff. Yeah.
On the picture, the water isn't spelled correctly.
Yeah, this is what AI does. I don't know why. AI gave me wind and earth, sort of fire and not really water. I don't know why.
That's Wicca water.
Isn't it weird? Because it's like I typed in earth, wind, fire, water. Yeah. No, because I can't control that. That's not something I can control.
So you make AI mouses like
yeah, I put rats in everything. Yeah. So we know that an element is a substance that cannot be broken down into simpler substances by what kind of means? Can't break it down, Annabelle?
Physical or chemical.
Very good, by physical or chemical means. Okay, so remember last week we talked about physical changes, which are things like melting and deposition and sublimation. Remember we talked about all those phase changes, and also things like crumpling up a piece of paper is a physical change, but that doesn't change the substance, right? And then chemical, we talked about chemical changes and signs of a chemical change, and that signs of a chemical change could be things like what? Give me an example. What's something that would give you a sign of a chemical change? What?
Like burning.
Yeah, like getting, well, what would be a sign that a chemical change happened if you burned something?
It will change into a new substance.
Yeah, changing into a new substance. So things like color change, production of heat, production of light, production of sound, all those things, right?
Yeah.
So these are what you would call chemical changes. So an element cannot be broken down into simpler substances by chemical or physical changes. So here's a point to make. You can break compounds down by chemical changes. So compounds are when you have elements that combine to form a new substance. For example, hydrogen and oxygen. You put 2 hydrogen and 1 oxygen together, what do you get?
Wait, what do you say?
2 hydrogen and 1 oxygen. Does anybody know what that
You
makes?
H2O.
H2O, which is? What's
Water.
it? Water. Okay, so if you put 2 hydrogen atoms and 1 oxygen atom together, you're gonna get water. No matter what you do to that water physically, it's still water. But can you break it down chemically? Can you break the hydrogen away from the oxygen? Yes, you can. And one way to do that is using electricity, and we're gonna do it this year. It's really kind of fun. So we're gonna use electricity to split water molecules into hydrogen and oxygen. And then when you do that, now the hydrogen has different characteristics from the oxygen because they're different elements, right? Okay. All right, elements. You can tell elements apart based on their characteristics. All right, so let's have a look here. Where in this image would you find the helium?
And like a.
Wait a minute, Everly. In balloons, very good. So that's where we're gonna find our helium. Helium has far lower density than our regular air, which is why when you have a helium balloon and you let it goes up. What's really happening is that the air below it is denser and the air above it is denser, and that air above it is sinking, and it's the sinking of the heavier, more dense air that pushes the balloon up. The balloon doesn't take itself up, it's getting pushed up by the air around it. Okay, how about where would you find gold in this image? Emerson, which one do you think? The necklace. There you go. All right. And Lucy, where would you find the copper, do you think?
I forgot what it's called.
This thing?
Thing
Like a
that-
kettle? Yeah, it's like a kettle or a teapot. Uh-huh. All right. And then how about iron? Where's that going to be, Emerson? The frying pan. Yeah. Anybody have a cast iron frying pan they use at home for anything?
Probably.
Mm-hmm.
I cook eggs with my all the time.
Ah, in a cast iron pan? That's great. All right. And how about neon? Where's the neon in this sign? Everly? In a sign. Okay. Neon is interesting. So neon, argon, xenon, there's a bunch of gases. And when we start doing the periodic table, you'll see that they're all over here on the right side of the table. They're called noble gases because they don't really interact. They're inert. They don't react with other things. They kind of stay on their own. But when you run electricity through them, they light up really bright like that. So we've learned to use them for signs. Okay, atoms. The basic particle for which an element is made is what? What's it called? Eunice? Yep.
A molecule.
No. Atom. Yeah, atom. Okay, there we go. All right, so how small is an atom? Okay, 3 to 10 atoms lined up will measure 1 nanometer. Well, what the heck is a nanometer? So the thickness of a nickel. Anybody want to guess how many nanometers thick a nickel is? Do I have a nickel? Anybody want to take a guess? Annabelle, what do you guess?
Maybe like a million or a billion.
A million or a billion? That's a big difference between a million and a billion.
Yeah.
Yeah, big difference. What do you think, Eunice?
How thick is a what?
A nickel, how many nanometers is a nickel?
1,000?
All right, let's see. It's 2 million nanometers. So 3 to 10 atoms, depending on the element, because some elements are bigger, their atoms are bigger than others. So 3 to 10 of them is 1 nanometer. And your 10 is gonna be your small ones like helium, hydrogen, stuff like that, right? And your bigger ones are gonna be where it would be 3. But look at this, you could line them up. And so you could get somewhere between like 6 million and what? 200 million, 20 million, sorry, 6 million and 20 million atoms would be the thickness of a nickel, and the diameter of a human hair is about 100,000 nanometers. So that's a lot. Yes, did you have a question?
Okay, I'm just like saying like,
Sorry.
there's this like, YouTube channel that teaches kids in a funny way, like there's a green puppet called Steve
Yeah.
and a blue puppet called Andy, and the YouTube channel is called Mr. DeMayo,
Mhm.
and every time like someone says helium in an episode, Andy pops down substance stuff from a balloon, and there's a bunch of weird
And then it
stuff
sounds weird. Yeah.
about Mr. DeMayo, like his only chance of reaching a million pounds is if he works for Subway, and that he sounds like a alien.
So does any,
Sorry,
sorry, I've got, yeah, this morning. Does anybody know why when people suck helium in, their voices sound weird? Do you know why?
Because of the way it works, like it makes your vocal cords and stuff move faster.
Yeah, yeah, kind of. It's because it's less dense than the air, so it does. It causes it to vibrate differently. Uh-huh.
One my brother saw like a bunch of helium
Mm-hmm.
from a balloon.
Mm-hmm.
And he fainted.
Yep, I was gonna say, if you do it too much or too often, it will cause you to pass out because you're taking in gas, but that gas doesn't have any oxygen in it because it's helium, not air. Air has oxygen in it, right? And you're taking in that helium instead of that oxygen, and your body thinks you're breathing, but it very soon realizes you're not. And then you can absolutely pass out. Yeah.
And when he woke up, he had an attack on his face.
Attack?
One of those things.
Oh no. Oh, a tick? A bug, or like the thing with the pointy thing on it? Attack?
The pointy thing.
Oh Lord, he fell and hit the floor and landed on it. Just keep tacks off your floor. Yikes. So if you could shrink yourself to the size of an atom, a single red blood cell might be the size of a mountain. Red blood cells are pretty good size too in your body. So, but they're still very tiny compared to everything else you've ever seen. But if we were to get out one of our microscopes, which we have, we could, and like prick somebody's finger, we could very easily find the red blood cells. They're very easy to see. And I may sacrifice myself next year for you so you can see that, because it's pretty cool to watch. Yeah. Yeah, you can see them for sure. All right, so when atoms combine, they form what? Does anybody know? Emerson? Yeah, well, chemical bonds, but yes, molecules is part of it. So we're getting there. So they form chemical bonds. That's how they combine. And they combine to form larger larger particles called molecules, which is what Emerson was getting at. So a molecule can contain multiple atoms of the same element or atoms of different elements. What contains only different elements? You know. Yes, the compound. Okay, so here's how it works. Oxygen is never by himself. There's never one oxygen atom floating around. They don't like to be alone because of the way they are chemically. They have to be with a buddy. So when oxygen is around, it's always in two. So it's O2. It's two oxygens. They join together. They hold hands. They're friends, and they go through life together like that unless they're split apart, because they never are alone. They just don't like being alone. So that is a molecule. It's not a compound because it's oxygen and oxygen. It's two oxygens. But water, H2O, because it's combined elements, you can call it a molecule, but it's better called a compound because it's got different elements. You have a hydrogen and an oxygen, and that makes it a compound. You cannot call the two oxygen together a compound. You can only call that a molecule. Does that make sense?
Yep.
Okay. And then we call things molecular compounds versus ionic compounds, and we'll be getting into that a little later, and you'll see that there's a difference. All right, so we're gonna play with some of these graphics for a minute. So
Oxygen.
this top one has one carbon atom, and then what do you think the other two are? Emerson. Two oxygens. Very good. All right. And then this guy has one oxygen and what, Lucy? What do you think?
Two helium.
Those aren't gonna be helium. They're real close though. What's another H?
Hydrogen.
Yep, she's looking on the back. That's what you do. Smart. Look right there and reference it. Look at the first thing on there, the very first one at the top left corner. There you go. She's got it. Hydrogen. What she just did is great. That's what you do. You're like, I don't know what that letter stands for. You look it up. You've got a reference on the back. You have a periodic table right on the back of your binder that you can look at any time. And you've got a bigger one inside your binder, right? Towards the end of your preface, you got a big one there. So one oxygen and 2 hydrogens. And what's this guy up here? This is the one we were just talking about. Eunice, who's this?
What?
What's
Oh,
this
the
one?
oxygen.
2 oxygens. All right, now, what's this one at the bottom got going on? What do you think that is, Annabelle? What's the big one here?
That's nitrogen and those are hydrogen.
Right,
ones.
nitrogen and hydrogen. Okay, so this tells you what is making up each of these molecules or compounds. All right, so many molecules and compounds have common names. Does anybody know what this one is called when you have a carbon and 2 oxygens together? Do you know, Lucy? No? You want to guess? Yes, that is exactly what that is. That is carbon dioxide. And how about this one where you have 1 oxygen and 2 hydrogens together? What's this one? Annabelle?
H2O, or in other words, water.
Common name, water, right? Okay. How about this when you have 2 oxygens together? Do you know, Lucy? You just oxygen. That's what we just said. So you're paying attention. Good job. And ooh, this one's gonna be tricky. Does anybody want to guess what this one is? It's a common name. You've heard it before. You've probably used it maybe when you're helping clean your house. Anybody, do you want to guess? Anybody want to take a guess? You want to guess?
So
Not so. This is ammonia. You ever heard of ammonia?
Yeah.
Yeah, it's in a lot of and it's in a lot of glass cleaners too. And right, it was in your book. Very good. So these are common names for these particular compounds or molecules. Now, oops, they also have formulas. I didn't mean to click that. So we said that this is C, and then 2 O's is going to be CO2. Now, here's the thing. You see where this number is tiny? Do you know what you call it when there's a tiny number like that? Do you know what those are called? There's a word for them. Anybody know? Do you know, Annabelle? Do you know what they're called?
well, so
Wait a minute. Before you say something separate, do you know what this tiny number is called?
it's like an amount of like one kind of atom.
Yeah, it tells you how many, but you know what it's called. Do you know?
Yeah.
Okay, so the word for that little number is a subscript. Sub meaning below. An exponent, which is up high, like we talked about scientific notation, when it's up above the number, it's called a superscript. So super meaning big or high, sub meaning low or below. So that is a subscript. So when we see our subscripts, it means there's that many of that particular atom. Now, when we get into balancing chemical equations, you're going to learn what are called coefficients, which are big numbers that go in the front. And that tells you how many of that compound, or that particular substance within a bigger compound. So
I see your camera.
you see my camera. Yeah, it happens. All right. So what's this one gonna, so this is the chemical formula. CO2 is our chemical formula for carbon dioxide. Everybody, what's the chemical formula for water? H2O. What would be? Yeah, so there are kind of standards for why we don't say OH2. And why in this case it was CO2. And you'll become familiar with them kind of as we go on throughout. Some of them just honestly flows better. Sounds like it makes more sense. So how about this one here? Oxygen. What is this one going to be?
O2.
O2 with a little subscript. You got it. And then ammonia is going to be, anybody want to guess?
H3N1.
H3N1. We're actually going to do that one the other way around. So it's going to be NH3. So we don't put ones.
Oh.
We imagine that the ones are a given. If the letter's there, it means 1. So we don't even bother with ones, but we do put subscripts for others. So NH3. See how it's NH3? Right. Okay, so all the atoms in these molecules are held together with chemical bonds. Ratios of atoms. What's a ratio? Anybody know what a ratio is? What's a ratio?
It's like 7 people are girls and 7 people are boys, and the ratio of girls to boys are 7 to 7.
Exactly. It's a perfect way to describe it. So a ratio is basically, it's a fraction. So if I said that in this room, 5 out of 6 people were girls and 1 out of 6 people was a boy, then we would know that our total is 6, right? And our ratio is 5 to 1, right? So it's a proportion or a fraction, and it tells you how many of something there is within a substance, for example. So if you're making cookies, and this is something we're going to get into called stoichiometry. It's a great word, but it's basically recipes. If your cookie recipe calls for 1 cup of sugar and 2 cups of flour, but you wanted to make double the amount of cookies, could you do 2 cups of sugar and 4 cups of flour? As long as you doubled everything, it's going to be the same. You can also divide it in half and it'll be the same. But what you can't do is do 5 cups of sugar and 1 cup of flour, because your recipe is not going to be right. Right?
Yeah.
Everybody agree that's going to screw it up? Okay. So you have to keep your ratios the same in a compound. Does anybody know how, and that determines what the compound is? It's the characteristic of the compound. So does anybody know how many carbons you would find in table sugar? You want to guess? So it's 12. How about hydrogen? Anybody want to guess? You want to guess?
12?
Not 12, 22.
Oh,
And anybody want to guess about oxygens? You want to guess, Emerson?
Yeah, I love
Good guess. Very good. There you go. All right. So 12, 22. So this would be C12, H22, O11, right? So ratios of atoms. Water contains how many hydrogen, everybody? How many hydrogen?
2.
2 hydrogen. And how many oxygen?
1.
1. Okay. But adding 1 more oxygen. So now instead of H2O, you have H2O2. You now have something completely different. It's not water, it's hydrogen peroxide. And peroxide is clear like water, hydrogen peroxide, and it's usually stored in a brown bottle, and you don't want to drink that, right? You can drink all the water you want, but you don't want to drink hydrogen peroxide. That's not good. So you have to be sure that you're keeping your ratios the same, or you're changing the substance. So your ratios of 2 hydrogen to 1 oxygen make water. But if you change that ratio of 2 hydrogen to 2 oxygen, you've got a different substance. Yes, ma'am.
How come you can't drink hydrogen peroxide? And like, what is it? Like, what is it used for?
It's poison if you drink it, but it's often used for like cleaning wounds. If you've ever had a scratch or a cut, and somebody puts, it usually comes in a brown plastic bottle or a brown glass bottle, and when you drip it on, it'll bubble and fizz when it comes in contact with the cut. That's hydrogen peroxide. And it's a great antiseptic. It cleans injuries, wounds really, really well. But you don't need to be drinking it. Not something to drink, right? Right. Actually, another thing to consider that's interesting is when you and we'll talk, well, actually I'll talk about it in a second, because I think it's going to come up in the other lesson, I think, not yours. Distillation. Did you guys read about distillation? No, it's in the other lesson. Okay. Distillation is when you take something and you take the sugar and you allow the sugar to ferment and produce alcohol, and you remove the alcohol from it. So this is like how they make liquor, right? That's how they make liquor and stuff like that. Anything that's considered a distilled spirit. So like rum, vodka, liquor, But in doing that, you produce 2 different kinds of alcohol, an ethanol and a methanol. The ethanol you can drink, you can consume it. You don't want to consume too much of it, because probably everybody here knows what happens if you have too much alcohol, right? It's not good.
It's like,
Yeah. Some people, well, usually it's more like, but yeah. So you don't want that, right? But methanol will kill you. So you don't want to drink that. So you actually have to, if you're doing a distillation for the purpose of producing alcohol, you have to know how to get the methanol and the ethanol separated. And back when COVID was at its peak, there were a lot of distilleries that made like whiskey and bourbon and things like that, who were producing tons of methanol as part of their production. And then it was a waste product and they didn't want it because it was useless to them up until COVID. When COVID hit, there was a demand for hand sanitizer. And so people that ran these distilleries were like, well, now our waste product can make us extra profit. So they would mix it with the stuff to create a gel, because it's great for hand sanitizing because it's still an alcohol, and an alcohol is going to denature protein membranes on bacteria and things, and it can help make a virus inactive. So if you, during COVID, if you ever got any hand sanitizer that smelled like a margarita or something, like I have one that literally smells like tequila, what it came from. It came from a factory somewhere where they were trying to get rid of the ethanol, and there's just a little bit of whatever left in it that makes it smell like whatever that particular product was. So,
My hand sanitizer smells like cherry blossom.
oh, now that's nice. Yeah, that's good. They probably added something good to that. So mixtures. We're going to be doing mixtures in lab today. So let's be sure we really understand what mixtures are. So a mixture is a substance made by, don't know who's calling me and I don't care, made by combining two or more different materials in such a way that no chemical reaction occurs. What cereal is that?
Lucky Charms.
I love Lucky Charms. It's kind of a guilty pleasure. I never buy it because I'll eat the whole thing. Yeah. So Lucky Charms. All right. This is a great example of a mixture. If I put a bowl of dry Lucky Charms in front of you and said, separate this into balloons, rainbows, unicorns, horseshoes, clovers, or whatever those are, leprechaun hats, and cereal pieces, could you do it? And would you be doing this by a physical means? Would you be separating it by physical or chemical process? Physical, right. So you got a mixture. You absolutely can. Now, it can usually be separated back into its original components. And now we have different types of mixtures. We have what we call, now this word is homogeneous. Some people will just say homogeneous. I tend to say homogeneous because that's what my teacher said and it kind of got stuck in my head. But we're going to watch a lot of videos with this dude, Professor Dave, who's like super cool and he does all these wonderful educational videos. And he says homogeneous, which is really more correct. So I'm going to try and say homogeneous, though it's hard for me. Because it's just in my head. It's just in my head, though, it's homogeneous. So homogeneous means where everything is evenly distributed. So your milk that you buy and get at home, if you buy cow's milk, okay, it'll say somewhere on the label that it is homogenized milk. That means that they have mixed it to the point where it doesn't separate. Because if it wasn't homogenized and you just milked a cow and put that jug of milk in the fridge, it would separate. The fat would go to the top, the liquid would go to the bottom, and it would not be one solid white milk. It would be in layers. So what they do is they shake it really hard, basically, so that it stays homogenized. So homogenized means that everything is mixed evenly. So homogeneous means evenly distributed, not easily separated. Did you have a question?
I'm lactose intolerant. I just want to say
There you go. That's no fun. So there are different types of homogeneous mixtures. We have the three big ones are solution, suspension, and colloid. Okay, a solution is when everything is evenly mixed and you can't see the different particles. Today in your lab, you're going to be using this solution, which is a mixture of sodium chloride, potassium nitrate, and water. Can you see the sodium chloride in here? Can you see it?
Yeah.
You can see it?
And it's not
Oh, no,
drinkable,
no.
right?
No. We're not recommending. No, you can't drink this. No. How about sodium chloride is just table salt? I mean, you could eat that, but not potassium nitrate. So can you see the potassium nitrate in here? No, it just looks like water, right?
Yeah.
This is because it's a homogeneous solution. A solution is everything is all dissolved equally. Solution has two parts, a solvent and a solute. The solvent is what does dissolving, in this case, water. The solute is what's dissolved. So in this case, table salt and potassium nitrate is actually the common word for potassium nitrate is saltpeter. It's actually used to dissolve stumps and make bombs. Really? Suspension is when you've got things that are mixed together, but usually there are larger particles moving throughout. And then a colloid is when you have things that are mixed together and usually you have one type of particle that surrounds another. A really good example of a colloid would be like mayonnaise. Mayonnaise is a colloid. It's oil and there's oil and water in the mayonnaise, but it's so well mixed that the oil molecules surround the water and it all kind of stays together.
I have a joke.
What's your joke?
What do you call a home scientist?
Oh, what? She's already laughing. What?
The homogeneous.
Oh, homogeneous. That is fabulous. I love it. I love it. That is really good. All right. So heterogeneous. Okay. So I want you to notice genius. Okay. In this case, what we're talking about is like a substance or a group. That's what genius is. It's coming in meaning substance, group, stuff. We have hetero and homo. Hetero means different. Homo means the same. So homogeneous means everything is evenly distributed. It looks the same. Heterogeneous means it's different. The things are different. They're easily separated. Okay. Separating mixtures. So we have different ways, and these are going to include, anybody know of some ways to separate mixtures? Oop, didn't mean to click it.
Like putting the piles, like, putting like a pile of
Mhm.
different fruits.
You can
like,
sort.
sorting them.
Sorting's one. What do you think he's doing here? We're using a funnel. What do you think?
Distillation.
This one's actually going to be filtration. Okay, so he's separating a mixture by filtration. So you're going to be doing this in your lab today. Basically, you're going to be taking that solution and pulling some crystals out of it by chilling it to a temperature where the potassium nitrate can no longer dissolve. It only dissolves at certain temperatures. And when it gets to a certain point, it doesn't dissolve anymore because it's too cold. You're going to get it so cold that it's going to solidify into crystals. And then you're going to run it through a filter and you're going to capture all the crystals. Yes.
Like in the video, we're gonna be using like an ice bucket.
Yes. Yes. You're going to use a bin with ice in it. What do you think he's doing to separate a mixture? Everly. Magnet. Yep. You can use a magnet. That's for sure. Some things are magnetic and other things are not.
Yeah, like sometimes like I used to put magnets in the sand and then like put some of the other magnets over there and like I would like search for the magnets and then they would come out of the
See if you
sand.
find anything. What's he do? Oh, evaporation was in the wrong spot. Look at my box was in the wrong spot. Sorry. Yeah, so he's doing technically I want to point something out though. Technically though, this isn't evaporation. It's not the best description of what's happening. Do you remember last week we talked about evaporation covered two different things? Evaporation, strike that. Vaporization covers two different things, evaporation and boiling. Technically, a better way to put this would say vaporization. And that's because you can boil to separate a mixture, which you are going to do today. And you could also let it evaporate. You could let it sit there. Actually, I've noticed that right on the top of this one that I just picked up to show you, it looks like some of my salt mixture got around the lid. And you can see right here where it's solidified around the top. And that's because it evaporated. It didn't get boiled. So evaporation is one thing, but so is boiling. So vaporization would be a better way to categorize this whole idea. All right, and then how about, this is the one I was talking about a minute ago. What is that?
Distillation.
That's distillation. There you go. I thought you guys had it. You see this little dude? Do you know what he's doing? So, do you know? Okay, Georgia history. Here you go. So back in the 1920s, the US government had a policy called prohibition. Who knows what prohibition was? So prohibition was when we had these people who were involved in what they called the temperance movement. Basically, everybody, or not everybody, certain people decided that alcohol in general was just bad. It was a vice and no one should be allowed to have it. They made a value call, a judgment call, and said no one should be able to have it because it's bad. Today, we still have prohibition. It's not for alcohol, but it's for certain drugs, right? We have drugs that are illegal, right? Can you bring like methamphetamine and just go buy it at the store? No, right? Can you buy? There's a lot of drugs you can't buy at the store.
And like
Those are
also-
illegal drugs. They're not good for you.
Like cocaine, right?
Like cocaine, not good for you. So because of that, they are illegal. The government's made them illegal. Well, there was a time period where the government made alcohol illegal. Okay, now alcohol is something that's been in culture for a long time. It's also part of certain religious practices. So making alcohol illegal was a lot harder than the government thought it was going to be. Because what happened is people started having like speakeasies, which are like clubs you could go down into some secret place, and that's where you could get your alcohol. It's also the reason for a lot of gangs like Al Capone, if you've ever heard of him. A lot of guys like up in the Northeast, there were gangs, like huge crime syndicates that moved alcohol because it was illegal, but there was still a demand for it. But down here in the South, we did what was called moonshining. Heard of moonshining? So moonshiners were guys who would build a still, which is a distillation apparatus. We have one of these for lab. It looks very different than the kind they use out in the woods. These guys would drive out into the woods in the middle of the night. And in Georgia, this was a really popular thing to do. And they would take things like wheat or potato skins or fruit. Basically, you can use almost any kind of vegetable because there's sugar in it, and that's what you need. And they would put it in a stew and they'd boil it and they'd go through this whole process and they'd create alcohol. Remember, they have to separate the methanol from the ethanol, but it's the ethanol they want. Usually moonshine is clear, but it's like very alcoholic compared to things like rum, tequila, vodka. It's much more higher concentration of alcohol. So these guys would put it usually in mason jars, and then they would sell it to people on the side, on the slide, because it was completely illegal to make it and to sell it. It's still illegal in most places to do moonshining out in the woods. These guys go way out in the woods because the federal agents would come looking for them. So they had to hide, right? So that's what these people would do. Now, here's why this is specifically interesting to the state of Georgia. So very often the moonshiners had to outrun the federal agents that had come to arrest them for making illegal alcohol. And in order to outrun them, they had to make their cars faster than the cars the government guys drove. And they would soup these cars up till they would go real fast around the mountains. That, my friends, is the beginning of NASCAR. You know NASCAR? The guys that race round and round in a circle?
For 25 days?
Yeah, that whole thing goes back to people in Georgia making illegal alcohol and trying to outrun the cops. That's how we got NASCAR. And Dawsonville, Georgia is like the birthplace of NASCAR, and probably one of the most famous NASCAR drivers that ever lived, Bill Elliott, is from Dawsonville, Georgia. They called him Awesome Bill from Dawsonville. So NASCAR and moonshiners running from the cops goes way back in Georgia history. And it's an interesting little piece of our history, because not every state can say, yeah, well, NASCAR belongs to us.
All this talk about Georgia reminded me about the song that played last night.
Oh, yeah?
The other night. My brother was playing guitar here. And at the end, he had to fight the devil.
Devil Went Down to Georgia. It's a fiddle song. Yes. Yes, that's the oh shoot, what's the name of it? It just left my head, the name of the band. Yeah. But that guy died. The leader of that band died like 3 years ago. So yeah, that's a fun song. Devil Went Down to Georgia. Yeah. So I want to end this lesson. This is from the TV show Moonshiners. Literally, this was a show. And it was on, I think, History Channel or TLC for a couple of years. I don't know that it's there anymore.
Is this legal to watch?
Well, here's the thing that's funny. There's no way the police didn't know they were filming this. There were film crews out in the woods with these guys in their stills.
Wait, is
So
it
this dude right here in the overalls, his particular moonshine that he was selling, it became, I think he was in Tennessee. But anyway, it became legal there to sell it. It is now legal to buy moonshine in a liquor store in Georgia. It's still not legal to make your own alcohol. You can make cider and beer, but you can't make distilled spirits. Like my husband makes cider and beer, but you can't make distilled spirits under the law in Georgia. I know people who do it, but you can't. But this guy, his particular brand, which you call Climax, something Climax, I don't know. Anyway, he now has a huge factory. He started in the woods with overalls in a barrel, and now he has a massive factory where he makes his moonshine, and it's distributed all over the country now. So you can actually like find it in his brand in the liquor store, which is kind of interesting. But what's funny about this is people watch this like these were real people and like it was a reality show. And I'm like, there is no way these people are not actors, and really good actors. Yeah.
Is it a movie or they just posted on YouTube?
No, it was a whole series. It was a television series. It went on for like 2 years.
Oh.
Yeah, there were many, many episodes of this. So if you watch these guys, I'm gonna have them going in case I need it. All right. So he's talking about how it works. So you can understand how distillation works here. Oh no, getting ads everywhere. I can't get away from it. It's all over. It just, you
Somebody's
can't.
voting ads.
There we go. I know, you can't get away from them.
Boom. Oh,
Pay attention to this.
sorry.
This is a cat that goes on the top of his pot. Put the cap on, like the lid, seal it off, build up the pressure. When he cranks this thing up to run it, you can hear it. It sounds like a jet engine. This then the vapor comes over to this thing here, the thumper, yeah. What the thumper does is it catches a lot of the big impurities the counter just comes up through the steel and doesn't turn into a vapor. Call this the thumper because when it builds up pressure, you get
That's how you get that. And what is this? It's the worm. Yeah, that's the worm, and it's acts as a condenser. This is the cold water.
Now, as the vapors come back over into here, of course, the cooling box has the worm set inside of it, and it's filled full of water.
And the effect of this going from hot to cold turns that vapor back to liquid. Yeah. So as we catch it and filter it here, then we put it in this tank here. You know, everything, all like that. We'll take all the alcohol out of here.
You
and put it
okay?
all in the proof.
Yes.
So it's kind of like consolidating the proof. Yeah, it's blending and mixing it to get one proof.
And that's when the little tricks of that trade will come into proofing. The first run will probably be about 110 proof liquor. So sometimes they'll cut it with some water. Generally, the end results will be about 85 to 88 proof liquor.
Now, real quick, let me explain what that means to you. Proof is a way that they measure the alcohol content of liquor. And proof is half the percent. Proof is double the percentage. So if you say something is 100 proof, it's 50% alcohol. To give you an idea, a glass of wine is about 6% alcohol. He just said his moonshine is 80 something proof. Yeah. That's why, that stuff's rough. All right, hang on. So see all those little jugs? That's not water.
And then you jug it up. If you do it all right, you should get about 10% of what you actually got.
From this 800 gallon pot, it can produce anywhere from 100 to 120 gallons per run. A lot of work, but they can do it.
Once the mash reaches 175 degrees, the alcohol contained inside turns to vapor. The vapor then travels through a pipe to the thump keg, where the alcohol doubles in proof. There, it bubbles through a small amount of moonshine held at the bottom of the barrel. The alcohol vapor then travels through another pipe to a coil of copper pipe that sits inside a barrel of ice-cold water, known as the worm barrel. Inside the coil, or worm, the alcohol condenses into the liquid known as moonshine. Finally, the moonshine is transferred to the proofing barrel, where it's cut with water and piped into jugs.
So, Georgia history. Yep,
What I have here is a model.
hang on, moving on. So, yep.
Legal to film?
Well, that's the thing. They made it out like the whole show was full of a bunch of illegal activity that you were getting to watch, but there's no way. There's a character on that show. If you're looking for something to do and you got 10 minutes, Google this guy, Jim Bob, something like that. I think his name is Jim Bob or something like that. He's this old mountain man who wears overalls, who's missing teeth. And they have to put subtitles under what he's saying, even though he's speaking English, because his accent is so thick, you can't understand him. He's like, and you know, huh? And they have to put subtitles for a man that's speaking English. Anyway, he's like the guru, and he's the one, Jim Tom, I think that's it, Jim Tom. But he's the one that everybody goes to when they need advice. So it's pretty silly. All right, so I want you to find lab 3 in your binder and take it out and tear it in half because you're not using it. You have a new lab 3, okay? Because it was missing some pages, and yeah, we're gonna undo it because it was missing some pages. So take it out, rip it in half so that nobody accidentally uses it.